Hello and welcome to part 3 of a video series on some 3D vector algebra from the IB Cambridge textbook. We have a problem that's very similar to the one we did in part 2. In part 2 we were given two vectors, and then we were given a third vector which counted as our direction vector. We had to add the sum of the two vectors where one of the vectors was scaled up in order so that the sum of those two vectors ends up being parallel to the given direction vector. The difference in this problem is the components of one of the vectors is q. That is to say, it's unknown to begin with. So sometimes we can't get a 3D rendering using graphing software, and in fact, if we're taking an IB exam, we won't be able to use the graphing software either. So it is important, however, just to draw a figure so that you can get a sense of what it is that we're supposed to be doing. We're going to be scaling up A, so in some respects what we're going to do is make A bigger or smaller, and it's yet to be determined, but wherever we put our scalar, it's going to make the direction of A the same. It'll just be shorter or smaller or whatever. So regardless of how we scale up the A, it's going to create a sum vector that heads off in any of these directions here. And that sum, that is to say this purple vector, should end up being in the exact same direction as the given vector. And so that's our goal, that's our objective, and even having a picture to refer to helps us understand the nature of the problem. The actual algebra here turns out to be really algorithmic, because all you have to do is substitute in the correct vectors into the equation, remembering, as I did explain in the previous video, that when we add these two vectors together, they should not necessarily be equal to the direction vector. They just need to have the same direction as the direction vector, which is another way to say it has to be some scaled version of the direction vector. Could be k could be less than 1, which means it's going to be smaller when we add these together than our given direction vector, or k could be bigger than 1. It doesn't really matter. But again, the algorithm is straightforward. Once we have all the vectors in place, we can just set up a system of equations. In this situation, it's a typical IB problem. They're able to assess your ability to solve a 3-variable system alongside your ability to work with 3-dimensional vectors. In this case, the 3-dimensional system is nicely designed for us to have only p and q in 2 of the equations, so that our first step is simply to write k in terms of p. I flew through this really quickly, obviously, because this is not a review of solving systems of equations. Feel free to pause the screen and read how I did this setup. Here I used the elimination method. I could have very easily used the substitution method, but it just sort of went with the flow quite nicely here. And in the end, I find out that the value of p is 3/8 and the value of q is 1/8. So the q represents 1/8, means that my direction vector for B is going to be pretty small of a vector, and the q value being 1/8. Oh no, that's what I just said, the q being 1/8, the p being 3/8 means we're actually going to make the A vector considerably smaller as well in order to get my two vectors to go in the correct direction. Moreover, we can see that if I subtract 1 minus p, I get my k value. Since p is 3/8, k should be 5/8. So here's how I can check my answer. By putting in the right values for p and q, I can get the A vectors already given. And the B vector is affected by that number q that we talked about. And here then we can see the scalar times A plus the new now known vector B, and we add them together. Do not be afraid of the fractions. It's all good. I end up with this vector, 5/8, 5/8, 10/8, which they all have a 1/8 in common, and I could also divide them all by 5. So if I factor out a 5/8, I get the vector 1, 2, 2, which was the direction vector that was given. And as we can see here, boosh, our k value is indeed 5/8. So that tells me that I didn't make any arithmetic mistakes here, and that it does confirm that I have the right values for p, q, and even k, a little side benefit. All right, that concludes part 3. We have 2 installments left. And now we're getting into the red zone. This is the kind of stuff that extends beyond the basics. In the first case, this is just a preview of the next video, we're going to look at this. Now, if you're looking at this out of sequence, you'll recognize this as a vector equation of a line. But in the sequence of the text, vector equation of a line has not been studied yet. And so what this question is doing is sort of preempting your understanding of vector equation of a line before you even know what you're doing. So it's a nice problem. So tune in.